Performance. After this section, you should be familiar with use of performance chart, airspeed indicator system calibration, ICAO standard atmosphere, stall speed, crosswind, takeoff performance, takeoff rate of climb, enroute rate of climb, cruise performance, landing performance, balked landing performance, noise data. Introduction. This section provides all necessary data for accurate and comprehensive flight activity planning, from takeoff to landing. The data presented in graphs and/or tables were determined using flight test data under conditions prescribed by EASA CSVLA regulations, aircraft and engine in good condition, average piloting techniques. Each graph or table was determined according to the ICAO standard atmosphere, EASA, sea level. Performance impact evaluations were carried out theoretically for variations in airspeed, external temperature, altitude, weight, runway type and condition. Use of performance chart. Performance data are presented in tabular or graphical form to illustrate the effect of different variables such as altitude, temperature, and weight. Given information is sufficient to plan the mission with required precision and safety. Additional information is provided for each table or graph. Airspeed indicator system calibration. In this manual, reference is often made to indicated airspeed, IAS, and calibrated airspeed, CS. Indicated airspeed, IAS, is the speed read directly from the airspeed indicator, assuming zero instrument and position error. Calibrated airspeed, CS, is the indicated airspeed corrected for position and instrument errors. It represents a more accurate measure of the aircraft's true aerodynamic speed. The graph shows the relationship between indicated airspeed, IAS, and calibrated airspeed, CS. As can be seen, the difference between the two values is almost linear across the flight envelope. Note: indicated airspeed assumes zero instrument error. Example: given an indicated airspeed of 75 knots, determine the calibrated airspeed with flaps up. Enter the graph from the left at approximately 75 knots IAS and draw a straight horizontal line until it intersects the solid line corresponding to flaps up. From this point, draw a vertical line downward to read the calibrated airspeed value. In this case, the calibrated airspeed is approximately 74.5 knots. For the normal operating range, from 0 to about 110 knots, the difference between indicated and calibrated speed is less than 1 knot and can therefore be considered negligible for most flight operations. ICAO standard atmosphere. The ICAO standard atmosphere is a model that defines average atmospheric conditions for performance calculations. It assumes a sea level pressure of 1013.25 hectopascal, a temperature of 15 degrees Celsius, and a temperature lapse rate of 2 degrees per 1,000 feet up to 36,000 feet. It provides a common reference to compare aircraft performance under standardized conditions. Within the aircraft flight manual, a graph is provided to determine the various parameters of the actual atmosphere compared to the standard one. However, the tables we will use later already include the necessary corrections to convert from the real atmosphere to the ICAO standard atmosphere. Stall speed. Please refer to the following table to review the stall speed values. Note that the stall speed has been calculated at the maximum takeoff weight of this aircraft and varies depending on bank angle and flap configuration. Note: altitude loss during conventional stall recovery, as demonstrated during flight tests, is approximately 350 feet with bank angles below 30 degrees. Crosswind. Maximum demonstrated crosswind is 15 knots. Use the following table to calculate the crosswind component for takeoff and landing. Example, you are taking off from Locarno Airport, runway 26, magnetic heading 256 degrees. The wind is coming from 290 degrees at 20 knots. The angle between runway heading and wind direction is 34 degrees. From the origin of the chart, draw a line inclined by 34 degrees to represent the wind direction. The wind intensity is 20 knots, so follow this line until it meets the 20-knot semicircle. From the intersection point, draw two perpendicular lines to find the headwind component and to find the crosswind component. In this example, the crosswind component is approximately 11 knots, which is within the aircraft's operational limits. Takeoff performance. Takeoff performance results are expressed in takeoff distances. The first value represents the takeoff ground roll, while the second indicates the takeoff distance. Takeoff ground roll, the distance the aircraft covers on the ground before becoming airborne. Takeoff distance, the total distance required for the aircraft to reach a screen height of 50 feet, 15 meters, after liftoff. As a general rule, before every flight, you must ensure that your takeoff distance is shorter than the available runway length. Both distance values are strongly affected by environmental factors such as temperature, air density, and especially wind conditions. To determine how much runway is available, you must check the aerodrome charts. To calculate your aircraft's takeoff distance, you must use the approved methods provided by the flight school, such as, in this case, the Aircraft Flight Manual, AFM. According to ALO Swiss Academy SOP, when calculating the takeoff performance of the TECNAM, you must always use the table corresponding to the maximum takeoff weight. Note: to account for likely in-service performance variations, apply a factor of 1.10 to all distance values. This means that, after obtaining the results from the table and correcting them for environmental factors, you must multiply the resulting distances by 1.10, effectively adding 10% to the calculated values. Please have a look at the header of the table. From here, we can see the conditions used to calculate the takeoff distances. In addition to these reference conditions, the table also indicates the correction factors to be applied for various environmental conditions such as wind, runway slope, or runway surface. All distances in this table are expressed in meters, m, while altitudes are given in feet, ft. Example: we are taking off from Locarno, runway 26 right. The outside temperature is 25 degrees Celsius, the QNH is 1010 hectopascals, and there is a 5-knot headwind. Let's calculate the TECNAM takeoff performance to verify that the runway is long enough for our flight. First of all, from the airport charts, we can see that runway 26 right is an asphalt runway, with no significant slope and a total length of 670 meters. The airport elevation is 650 feet. Now let's move on to the Aircraft Flight Manual table, but before proceeding we need to do a calculation. The reference for the altitude used in the table is not the field elevation, but the pressure altitude. The airport elevation and the pressure altitude differ if the QNH is not equal to 1013 hectopascals. We use the following formula to calculate today's pressure altitude. The QNH was 1010 hectopascals. The result of the formula is 741 feet. For convenience and to be more conservative, we will use 1,000 feet when consulting the table. Now we consult the table with the outside air temperature, which was 25 degrees Celsius. We obtain a takeoff ground roll of 267 meters and a takeoff distance of 442 meters. However, we now need to apply all the applicable corrections. For the wind, since there was a 5-knot headwind, we need to subtract 25 meters. Since the runway is paved with asphalt, we can reduce the distance by 10%. The runway is level, so there is no correction for slope. Don't forget to factor everything by 110 as required by the aircraft flight manual. The final result is 266 meters for the ground roll and 459 meters for the takeoff distance. Since the takeoff distance is less than the distance available on the chart, we can take off. Takeoff rate of climb. Tecnam has published 2 tables to calculate the initial climb rate after takeoff. The 2 tables cover 2 conditions, with flaps in takeoff position and with flaps up. Notice how, as the pressure altitude increases, climb performance decreases drastically. Note, to account for likely in-service performance variations, apply a factor of 0.90 to the rate of climb. In accordance with the SOPs of ALO Swiss Academy, the climb is conducted at the best rate of climb speed of 68 knots. Enroute rate of climb. A different table is used for the rate of climb during the enroute phase. In this table, no flap positions other than up are considered. Cruise performance. For the cruise phase, the most important parameters to calculate are the fuel consumption and the aircraft range. These parameters depend on the engine power output, expressed in RPM, and on the aircraft altitude, expressed as pressure altitude. In accordance with the SOPs of ALO Swiss Academy, the hourly fuel consumption to be considered for the Tecnam is 20 litres per hour. Caution: propeller speed over 2265 RPM is restricted to 5 minutes. As shown in the tables of the aircraft flight manual, the hourly fuel consumption depends on the power setting, the pressure altitude, and the outside air temperature. The table includes the terms endurance and range. Endurance: the amount of time the aircraft can remain in flight based on the fuel available on board. Range: the distance the aircraft can cover with the fuel available on board. The tables do not take into account wind components that may be encountered during cruise. While endurance is not affected by the wind, range is significantly influenced by it. A strong headwind can greatly reduce the aircraft's maximum range. Landing performance. This topic is very similar to takeoff. To evaluate landing performance, 2 distances are considered: landing distance and landing ground roll. The landing distance is the distance the aircraft covers from a screen height of 50 feet to a complete stop. The ground roll is only the distance the aircraft travels on the ground. To operate on any runway, you must ensure that your aircraft's landing distance is less than the landing distance available. The calculations to determine the landing distance are very similar to those for the takeoff distance. Refer to that section of the video to understand how to proceed within the table. However, it should be noted that the factors indicated in the table header are different. Note: to account for likely in-service performance variations, apply a factor of 1.67 to the distances. Balked landing performance. A balked landing is a go-around initiated when an aircraft has already touched down or is within seconds of touchdown, often due to issues like an unsafe approach, a long landing, or obstacles on the runway. Unlike a standard go-around, which happens higher up, this is a very late-stage decision made to avoid a dangerous situation and start a new landing attempt from a safe altitude. Refer to the following table to define the rate and angle of climb after a balked landing. Note: to account for likely in-service performance variations, apply a factor to rate of climb and to angle of climb of 0.90. Noise data. Noise level, determined in accordance with ICAO Annex 16 6th edition, July 2011, Volume 1, Chapter 10, is 6983 dB. This concludes the video on aircraft performance. In the next video, the topic of weight and balance will be covered.